Cloud.
So are we good to get started? All right, then we'll start a minute early. So first of all, welcome everyone. Thank you for coming. This is our first Coffee and Conversations, I think is the title, speaker series hosted by ICDT. Hopefully the first of many to come for this spring semester. So make sure to check out the ICDT website for upcoming events and consider signing up for the mailing list. It's my pleasure to introduce today Michael Brown. He's a principal security engineer at TrailofBits and also a PhD student, somewhat perpetual PhD student at Georgia Tech, which is where he and I first met. TrailofBits is a small business that does a lot of research and engineering and services for the Department of Defense and others. Michael's primary research interest is in the development of software transformation techniques to improve the security of computer systems. Prior to his work in software security, he was in active duty for 8 years for the U.S. Army, where he served as a UH-60M pilot. Hopefully that's how people say it. And also an aviation mission survivability officer, which I'll have to ask you what that means. He earned his master's in computer science from Georgia Tech and his bachelor's in computer science from University of Cincinnati. So if we're ready to go, whenever you're ready, the floor is yours.
All right. So it switched over right as he was talking to use the.
Did you switch me back by any chance?
I have no idea what happened. So.
Still seeing you here, so. It's back online.
Okay.
So. Which do my keyboard?
Might also want to make sure everyone on the Zoom can hear us. All right, I think we got it worked out. Hi, everyone. Thanks for the introduction, Carter. So, as Carter mentioned, I'm a principal security researcher at TrailofBits. Also, have been doing a PhD for a long time at Georgia Tech. And what I'm here to talk about today is some work that I've been doing over the last almost 4 years now on using graph-based machine learning algorithms to solve challenging problems in software analysis. So before we move on, is there anyone on the Zoom? Do we see if they can hear us? Okay. If someone on Zoom can write a message in the chat or something, let us know if you can hear me.
Yes, you're audible.
Yeah, they might not be able to. I think I need to turn my microphone on.
Yeah, and they can't hear us, and
If you're on the Zoom, can you let me know if you can hear me?
We can hear you.
All right, so let's just jump right in. So let's talk a little bit about what software analysis is. So when we do software analysis, our goal is to automatically elicit or determine program facts. And these facts are usually what the program does when it's run dynamically, what kind of behaviors it exhibits, what kind of security posture it has, etc. Software analysis is used very extensively in several fields. Okay. We'll get there. So I think if I swap that, I'm gonna have to.
So if you go to,
Tell you what I'll
just
do.
stop the
Let me
share.
Just bigify this. So I should be able to see the screen. And I can see it there too. As I started. Okay. All right. I think this will get it done. All right. So there's only one slide, and I'm just gonna start over. So. All right, so when we do software analysis, our goal is to try and automatically determine useful facts about programs' behaviors or its properties. We use this extensively in compiler technology, in the security industry, and also in reverse engineering. But due to the inherent undecidability and computational theory that underpins a lot of this, unfortunately, we know going into this, we have to make trade-offs. We know that it's undecidable in the general case for us to collect a complete set of program facts in the general case. Small, simple programs, we might be able to, but in general, we're not going to be able to understand either from static program analysis or dynamic analysis, the full set of properties and behaviors of a system. So this ultimately means that there are many core problems that we can't deterministically solve in software analysis. So in compilers, this crops up in what's called phase ordering. Most of you know that your compiler, when it takes your source code and turns it into a binary or into bytecode, it tries to optimize it to make it run as fast as possible. And to do this, they use modular optimization passes on the code to incrementally refine it. But there's a big problem in that determining what order to run them in the optimal manner is undecidable. So we kind of just have to look for the best sequencing empirically and go with it. When we're talking about reverse engineering, this means we're not going to get precise binary decompilation, meaning that if we're trying to take a piece of legacy software, figure out what it does so we can improve it, we know going in that we're unlikely to be able to recover the full binary in its full set of program facts. And then finally, in security, the undecidability of program analysis also means we're never going to be able to say that a given program is vulnerability free. It's impossible to state this. It ultimately reduces to the halting problem. And this creates a lot of issues for us, mainly because we've been studying software analysis very intently for the last 25 years or so. And where we stand now, meaningful gains are really few and far between. We've gotten to the point of diminishing returns with software analysis where we study for years and years and years to make really incremental improvements upon technology that had existed, back in the early 2000s. So the way we've made these incremental improvements has been to employ heuristics to rely on humans in the loop to be able to solve some of the fuzzy problems. But ultimately, this doesn't scale because there's only a limited number of human experts. So you got a question?
What is phase ordering?
So phase ordering is a problem in which you try to determine what's the optimal sequence of optimization steps in a compiler. It crops up in other related domains, but essentially, if you write an optimization pass on software that tries to, let's say, use less memory, or one that tries to speed up execution, they both are working on the same program, and it's impossible to tell a priori which one you should run first to get the optimal result. All right, so even though we've hit the point of diminishing returns with conventional software analysis, the focus of my research has been on trying to get past these using AI and ML techniques. And the reason why we can do this is artificial intelligence or machine learning is not bound by the constraints of traditional software analysis. So in traditional software analysis, we have to deal with computability theory, which is a prescriptive problem. But when we deal with AI and ML, we're dealing with a descriptive problem, where we show or we create a model from a large number of examples, and we try to teach a model or try to make a model learn how to solve a given task based on what it's seen before. So this is great because it approximates the human problem solving for fuzzy tasks that we're already trying to use humans in the loop for. And we know going into it that if we try to compute using a deep neural network, which is what is artfully depicted here on this slide, we know going into this that we're going to be able to, sorry, this just muted on me. We know going into it, we're going to be able to compute an inference on a machine learning model. We might not be able to compute an answer with traditional software analysis. But there are a number of challenges with trying to apply artificial intelligence, machine learning techniques to software analysis. One is, how do we even represent software in a way that ML techniques can ingest? ML techniques are made for static data. It's made for things like housing prices. It's made for things like time sequence data. It's not meant to look at programs that have dynamic properties when executed. So yes, you can take a look at a file, a program on disk, and it looks like static data, zeros and ones. We can represent it in a very static way, but ultimately that's not how we use software. We execute software. It has dynamic properties that oftentimes we can't determine. So we need to make sure that when we do AI ML modeling, that we're doing this in a way that is cognizant of those dynamic properties. Second, we have to understand what's the right program representation to use. Talked about a number of different problem areas, different areas that consume software analysis. Compilers work with the entire stack of program representations. They take something in source, they convert it to an intermediate representation, and then they output a binary. When we're dealing with software security, a lot of times we're dealing with binary only. We're dealing with software that's been obfuscated and we don't have access to the source code. Conversely, in the number of security problems, if you're on a blue team, you're trying to actually secure software, you do have access to the source code. So there's a question going in of what's the right program representation to use. And ultimately, there's two major pitfalls as well. The first of which is making sure that you're actually applying machine learning to suitable problems. Software analysis, one of the key properties that we need for a lot of different software analyses is soundness. We need to make sure that whatever we're doing to the program maintains its integrity. So for example, if we have a program and we want to perform some software analysis or some transformation on it, some paths to improve it, and let's say fix a security vulnerability. If we fix a security vulnerability, but we otherwise compromise some other function of the code by changing it without making compensatory transformation somewhere else, we can introduce new vulnerabilities we don't know about. And essentially, we've traded a known vulnerability for an unknown vulnerability, which is a decidedly negative trade-off. And lastly, can we get enough data? All descriptive machine learning techniques, supervised machine learning techniques require lots and lots of data because we're trying to teach this model how to deal with novel versions of a problem by looking at prior problems. And as we all know, and just as the general case for learning, experience matters. The more versions of a problem you've seen, the better equipped you are to handle a new problem in the future. So I'm going to go through some of the key insights that have come out of my research on this topic. And the first, and these roughly correspond to the four things that were on the previous slide. So the first is, how do we represent software in a way that machine learning techniques can ingest? So one of the things that we noted very early on is that programs are inherently graph-like. What you see depicted on this slide is a screenshot from IDA, which is a reverse engineering tool that takes a binary and represents it such that a user can try to figure out what that machine code is doing. As you can see, it looks like a graph. This is what's called a control flow graph. This represents blocks of instructions and then the potential new blocks of instructions they can branch to based on things like your control flow behavior, your conditional behavior within the program. So one of the things that we can do is we can represent programs as graphs, which capture some of their dynamic properties. Meaning if we execute the instructions in block A, we could potentially go to block B or block C, depending upon a conditional check at the end. We capture some of these dynamic elements. And also it's very convenient that graph-based machine learning algorithms exist. So we don't have to come up with unique or novel modeling techniques. We just have to adapt ones that exist for other graph-based problems. Second is deciding on what's the right program representation to use. Our insights here is that this really depends on the application. The two projects I'm going to talk about today that were performed under funding from DARPA, we had to use different levels of software representation to solve the right problem. So in this case, using and reusing compiler technology is really useful. And the insight here is that we can use these technologies essentially as data preparation tools. So most people will use Excel or NumPy or Pandas as like a data preparation tool in their ML applications. When we're dealing with software, we can use the compiler because the compiler is already used to reading software in at certain levels of representation, changing them, extracting facts, which we can use as learning features. All right, last or third, referring back to picking suitable problems for ML-based approaches. We can't expect machine learning systems to be 100% accurate. Therefore, the most important thing I want you to leave here today with is don't use them when you expect soundness. So for example, if a compiler is trying to optimize code and make it run faster, if you can't be sure that the analysis and transformation you've done in the code hasn't broken the program, then you shouldn't use it. This is a tenet of conventional software analysis, but we know going into it that using an AI or ML system, we're performing inference. It's going to be subject to some amount of error, some amount of misclassification. So we shouldn't even try to use AI ML to try and optimize programs. We should make sure and do a litmus test essentially before we try to apply this. Otherwise, you end up going down a very fruitless path, which, in my opinion, a large sector of the tech industry is currently doing, trying to use large language models to solve soundness properties of programs. For example, finding vulnerabilities in code and other things. Large language models have proven with a high error rate to be very poorly suited for these tasks. All right, the last key insight that you'll see from our work is referring to getting a sizable amount of data. So real world data is really hard to find in volume, particularly for security tasks. The data is unstructured. It's not collected in a consistent way. And this makes it really challenging to build AI and machine learning models for software analysis. But we do have a large number of tools that have been built, or a large number of research projects focused on automatic program generation. This is for doing things like compiler testing. This is for doing things like automatically generating unit testing during software engineering. So we can use these tools to create synthetic data sets. And if we do this in a way that is representative of the real world, we can amplify or create data where we don't actually have structured data. And this is something that we had some success with. Sure.
See, you mentioned that that using LLM to find program vulnerability is not a good idea.
Yes.
But I think there is no need of the soundness, right? Even if it does not find a vulnerability or find a little hint of the vulnerability, that it should be good enough. But I did not understand why you mentioned that.
Oh, so perhaps I should expand that to say asking an LLM to find a vulnerability and generate a patch for it. Generating the patch or trying to patch the program does incorporate some of the soundness properties. It's more referring to the high error rates with vulnerability discovery, and LLMs are poorly suited for that, mainly due to that task. And also in the security industry, we care much more about novel vulnerabilities, undiscovered vulnerabilities. When we deal with known vulnerabilities, that's a patching problem. Most of the time, that's the users just haven't applied their patches or applied their updates. So dealing with novel vulnerabilities, LLMs have very poor capability in general to generalize to novel vulnerabilities or new examples of problems, mainly because they're not actually trained specifically for vulnerability discovery. They're trained for wide-scale text processing. So the same model that you use to tell you a good recipe for waffles is the same model that you're using to tell you whether or not a given program has vulnerabilities within it. So those are some of the underlying issues. By the way, I've only prepared about 40 minutes or so of talk time. So please ask questions along the way. Please don't hold them till the end. There's a lot of stuff in here. It's changed topics a couple times. So, all right. So teams that I've worked on have been successful on 2 projects in recent years using graph-based machine learning algorithms. These 2 projects were funded by DARPA. The first, we created a tool called VulChecker, which helps us find vulnerabilities in source code files. And then 2 was Corbin, which was a project that helped us recover symbolic mathematics from binaries. So the first problem is decidedly a security problem. The second problem is a bit more of a compiler problem, a bit more of a reverse engineering problem. So I'm going to walk you through how we approached both problems and what we learned. So let's start with VulChecker. So certain types of high-risk vulnerabilities are really difficult for traditional code scanners to discover. And we wanted to know if ML systems could do better. A good example of this is an integer overflow. If you're making a ring-based addressing for data structures, then integer overflow is an aspect of computing that you'll exploit to make an efficient data structure. In almost all other instances, using an integer overflow or having an integer overflow occur in a program is usually a bug at the very least and a security vulnerability in some limited circumstances. So this is a type of vulnerability that traditional code scanners do very poorly on. They have rule-based semantics that can't tell if you're trying to use it as a feature or if it's a bug. And they also can't tell if it's a bug that's going to be exploitable. So they have high false positive rates. So looking at this problem, let's refer back to our first pitfall is, are we actually using a suitable, or is this a suitable problem for ML? And the answer is yes. It's because we have no requirement for soundness, as you touched on earlier, because existing code scanning workflows already have false positives and we're already tolerant to those. We already know that when we use a rule-based or conventional software analysis tool, we're going to have to verify manually that those alerts are correct. And then second, will we have enough data? And the answer there is also yes, because we can use existing data sets and benchmarks as training data, but that actually turned out to be not as simple as we had thought.
Would you like to develop a little bit more, because why it does not require soundness? Is it because the traditional techniques themselves produce false positives? So the problem itself is not that sensitive to the false positive?
In this case, the clarification I made earlier also applies. When we're trying to find vulnerabilities, we're not also trying to transform them. We're not trying to patch them as well. So in this particular case, we're trying to replace existing code scanning tools that already have false positives. If we're trying to actually generate patches for these with an AI model, then soundness would be a problem. All right, so let's take a look at how Volchecker works at a simplified overview. On the bottom, you'll see the deployed version, and at the top you see the training model. So what we do is we take source code that corresponds to programs that have vulnerabilities. We have labels for that data as well, which label the manifestation point and root cause points for the various vulnerabilities contained within the code. We take this data and we process it with the LLVM compiler. So these are vulnerabilities that are in C and C++ source code. So using the compiler, we're able to lower from source code, which is a very contextually rich program representation, to one that's much more straightforward to process with machine learning, which is LLVM-IR, or an intermediate representation. This is the intermediate representation that the compiler uses to optimize code. So it's much lower level. It's not quite as obtuse as machine code, but it's pretty close. So ultimately, from this stage, we create what's called an enriched program dependency graph. We're creating a graph-like structure that captures the static and dynamic properties of the program. And we then place this through a couple of ML components that actually create a model. Now, we reuse some of this architecture when the model is deployed. And the user story essentially goes as such. The user will have some source code that they're writing through a plugin in their IDE or some other interface. They will send this code to be scanned for vulnerabilities. It will be processed using the same data processing pipeline, only there won't be labels this time. We'll be doing inference rather than training. We'll query the deployed model to ask it if it finds any vulnerabilities within the code. It generates vulnerability alerts that are fed back to the user, so the user can repair their code before they try to submit it as a pull request, or if they're doing an audit, they can put that into their findings. So let's talk a bit about how we use compiler infrastructure to actually do this conversion. So if you take a look on the left-hand side, you'll see a relatively short snippet of C code. When we convert this to a program dependency graph using the LLVM compiler, we end up with a set of nodes. Each node corresponds to an instruction and a set of edges. Each edge represents dependencies between instructions. So the black arrows you see depicted here are control flow dependencies. A control flow dependency from one node to another indicates that the second node is an instruction that's executed after the first. You'll notice here, for example, that after this particular instruction, which is a conditional branch, we can either execute this instruction or that instruction. This is one of the ways in which we capture some of the dynamic properties of the code rather than just looking at it as a sequential sequence of text lines. The orange lines you see depicted are data flow dependencies. What this means is that a value or a piece of data that's produced at one instruction is consumed later by another instruction. And you'll see that these aren't necessarily in order. So for example, when we allocate an integer in the very first line of the program, using the line in a equals 0, that value is not actually consumed until two later instructions, both of which occur after the conditional branch. So in this way, we're also catching the dynamic data flow properties of the program, rather than once again looking at this as a sequence of text tokens like large language models and other prior models based on BERT attempted to do. All right, so now let's talk about the actual data we used. Originally going into this program, we had hoped to use Juliet, which is a data set provided by NIST. It's a bunch of small toy programs that have code comments in them that label where a vulnerability exists in the code. They also oftentimes label where a vulnerability root cause point is located. So this is useful for our strategy. The problem we ran into is that ultimately all of these all of the sample programs in the Juliet data set were really low fidelity. They were synthetic toys. They didn't look like real programs. But like I said, they were really low effort because they came labeled. We had to do relatively minimal processing to get labeled data. There was high contrast because one of the features of this data set is that you can, using a preprocessor flag, you can process the code to produce a vulnerable version and a patched version with the same piece of source code. So we're able to generate lots of no samples and lots of yes samples for there being a vulnerability. And also there's a large volume. We had thousands of these and also they covered a large number of different types of vulnerabilities or CWEs. So because of these properties, we had hoped to augment our data set with some samples from the real world that we would scrape from GitHub. In contrast, these samples, there's a lot fewer of them because we have to use things like a MITRE CV database to try and find them. The data is not consistent, so the number of samples we could pull was relatively low and it required a lot of effort to do, but these samples are high fidelity. They look like real world programs because they are real world programs. Unfortunately, we couldn't automatically find the patched and unpatched versions for most of these samples, so we had samples that were low contrast. Which ultimately led to a number of issues with our data set. Specifically, that the small number of real world samples weren't enough to help the model generalize, and we originally got poor results. So we had to take a different tack, which was doing synthetic augmentation with the data. What we did in this case is we essentially found a way to combine and transform, once again using compiler infrastructure as the muscle to do this. So essentially what we would do is we would take nodes, the relatively small short toy example of a vulnerability from our synthetic data in Juliet. We would take these nodes and we would insert them into a large real world sample of code that we knew didn't contain any other vulnerabilities, or at least to the best of our knowledge. And what we end up with, if we do this in the correct way and we maintain the right relationships, is we end up with a vulnerability that is in code that looks like it's real world, but we have a representative version of that vulnerability injected. So with this augmentation data, rather than trying to use both sets of data as a single training data set, we actually merged them to create a data set that had the best of both worlds.
Yeah, quick question.
Sure.
So the process of synthesizing examples, I mean, how do you ensure that the result is a meaningful program?
Okay.
You take a slice of one synthetic small, presumably whatever,
Yeah.
automatic generated example, and put it in a real program.
Mhm.
You know, that always creates a question.
Yeah, so this is one of the benefits of using compiler infrastructure. So we are doing all of this work at the LLVMIR level. At this level, things like variable names have no meaning. They exist only to help us read code better. You can replace all the variable names in any program with A, B, C, D, 1, 2, 3, some version of this, and it doesn't matter. In fact, it's actually a well-known code obfuscation technique. So when we convert these instructions and their dependencies into when we convert these instructions into LLVMIR, all of that extra information goes away, and it becomes much easier to work with the code. So for example, all we have to do to maintain a meaningfulness or make this program look as if it's meaningful to, at least to the model, is make sure that one, reachability is maintained, and two, that data flow is maintained. Essentially, the edges need to be reasonable and need to be maintained. So if you take a look here, the red nodes the set is essentially a small path. The first node is the root cause point, and the last node is the manifestation point of a vulnerability. So by splitting these nodes across, we have to make sure that these two nodes have a reachable control flow path to the actual vulnerable nodes. And we also have to make sure that the data flow dependencies are maintained. This is actually done for us automatically because compilers convert code into what's called static single assignment form. They get rid of all of your notion of reusing the same variable over and over again. They instead use a much simpler notion of data flow, which is I have a value that I create, it's consumed somewhere else, and every value is created exactly once. So you don't actually redefine the variable at the same time over and over. So this is getting a bit into the weeds, but ultimately, yes, we have a strong argument for why these represent vulnerable, or why these represent reasonable programs. So this would essentially be like taking a vulnerability that consists of 4 lines, inserting them into one place, putting the other code somewhere else, and just making sure that the data flows don't interfere.
So, I mean, that does make sense as far as these very sort of coarse-grained types of programs, such as control flow, readability, and some simple forms of data dependency. But the subtleties of the actual semantics and what the semantics does to trigger particular vulnerable behavior that you're trying to take. That goes way beyond, the fact that there's a, get-user relationship between two of them. Right? It's about some, I mean, people have obviously symbolic execution of million other types of things to get to the somewhat more precise model set. So I'm just curious as to, I could see this being useful for learning, training some kind of model to some degree, because it does provide sort of more contextual structure in which these vulnerable pieces would appear, and this would make the model somehow more possible. But still doesn't quite get to the question of, are these actually legitimate programs?
So the good news is they
Because
don't have to be.
semantics.
They don't have to be.
Okay.
Because I'm never gonna run this. It's training data. Its lifetime ends once it's ingested by the model. So part of our argument here is that we actually don't care that we performed a destructive transformation, because it exists solely to allow a machine learning model to generalize to a problem and make meaningful alerts to a user.
I could see how this argument would hold if your learning itself is based on simple things like control flow and data flow, and not on some deeper structures related to some abstract interpretations. Is that the case? Are you sort of assuming that the learning itself is based on primarily control flow and data flow, and not on anything more complicated than that?
For the different types of vulnerabilities that we train this model to identify, the answer is yes. This technique's not going to generalize to every single CWB type. So your point's well taken. It's not going to work for things like heap grooming. It's not going to work for things like heap-based upper flows, where you're dealing with like machine model semantics that aren't captured in the software. For those types of operations, you'd have to augment this further beyond control flow and data flow with some kind of memory model for the program. So you're right. The answer is that you're not going to capture everything with this, but we are trying to capture something with this. And for the types of vulnerabilities we looked at, we were successful with these. So yes, there's more work to do. There's more ways to expand upon this. It's not a catch-all solution. But yes, you're right. It's generally not feasible to identify every type of software vulnerability. For example, we can't catch logic bugs with this. If you write your code and there's some way to access the protected function without authenticating, and there's no actual fundamental like problem with the machine model, we're not going to catch that. But also no static analyzer catches that either. So in terms of achieving the state of the art, we really just have to improve upon the failures of existing techniques as opposed to, creating a solution that's all encompassing. So yeah. Okay, so now that we've talked about how we created the data, let's talk about how we actually process it and turn it into training samples, and how we actually create a useful model from this. So starting with what you see on the left, we capture the first couple of stages of this, where we take the source code, we convert it into a enriched program dependency graph. As I mentioned before, we are modeling vulnerabilities as a path through the program that starts at a root cause point and ends at a manifestation point for a vulnerability. So this is defined differently for different types of vulnerabilities. So what this means is we have to train a specific model for each type of vulnerability we want to recognize. So what we do is we take the original program dependency graph and we take cuts, we take slices between the root cause points and the manifestation points. So we're dealing with training data. These are labeled, so we know what they are. But also, our EPDG production process, it also labels all possible manifestation points and possible root cause points. Once again, this is dependent upon the individual CWE. So by performing these graph slices, we essentially can sample from a single graph many different possible vulnerabilities, many possible paths from a possible root cause point to a possible manifestation point. So we can take these, for the ones in training data that we know aren't real manifestation points and aren't real root cause points, we can label these as benign samples. And for the paths that exist between true root cause points and true manifestation points, we label these as malicious samples. We can use these to train binary classifiers that are based on deep neural networks. We use a library called StructureDVEC, which actually creates the machine learning embeddings from the graph structures. And ultimately, we train these models to either classify a novel sample, which once again, we perform graph cutting to take a novel or an unlabeled sample between possible root cause and possible manifestation points. And essentially converting that to the embedding, the binary classifier will say this is vulnerable, this is not vulnerable. Now, because we've maintained debug information throughout this process, even though we're looking at something in LLVM-IR and compiler land, we can relate that back to the original source lines of instruction to give a meaningful alert to the user. All right, so let's talk about how we evaluated this. So we compared VoltCheckr against 4 other machine learning tools. Some used natural language processing, essentially BERT-based models, and also a single commercial SaaS tool. So this is something that companies pay for to help them find vulnerabilities in their program. And we looked at these 5 competing tools, and we looked at this across 5 different CWEs. And ultimately, we determined that VoltCheckr outperformed the state of the art for certain CWEs and performed no worse than existing tools for some CWEs. So summarizing this in the interest of time, for certain vulnerabilities that are well-defined, like stack-based buffer overflows, VoltCheckr did about as well as commercial tools and other ML tools at identifying these. But for certain sticky types of bugs, like integer overflows, where the presence of a vulnerability is very context dependent upon the programmer's intent and the actual ability for that to be overflowed in a meaningful way to constitute a vulnerability versus a bug, VoltCheckr outperformed those tools by a wide margin. So
Is VoltCheckr open source?
it is. It has been made available. It's very hard to use right now. One of the things that my company is doing over the next few months is we're incorporating this both into our work on DARPA's INGOTS program and our work competing in DARPA's AICC. VoltCheckr will hopefully be a part of both of those. So I hope to make a second version of VoltCheckr that's much less of a pain to use. So it is out there, but I would warn you to have a large pot of coffee before you start trying to use it, because it's quite complex.
Quick question.
Sure.
How important is the augmentation in achieving rates?
It's very important. These results were after augmentation. So this is reflective of a research failure in which trying to use a data set that was essentially low fidelity and high fidelity data kind of just concatenated together and thrown at it. We didn't get very high contrast results. So the data augmentation process is how we were able to achieve essentially achieve this difference or this improvement over the state of the art. All right, so next, with the time we have available, I'm going to talk about CORBIN, which is an acronym that stands for Concept Recovery from Binary. This is another graph-based tool. This was a follow-on program or a spiritual follow-on program to VoltCheckr. Only this is adapted for a much different problem. So this problem, legacy cyber physical system software, you can think of this as like the firmware that runs an electric turbine in a windmill or in a solar panel system, or some kind of electric regulator, some kind of embedded firmware. It needs patches in order to improve its performance or improve its safety margins, et cetera. But as is the case with a lot of embedded software, a lot of the companies, they go extinct. They go out of business after deploying software, or they don't sell their software to their clients because they want to vendor lock them for updates later. So this presents a big problem, particularly for the US government, because it can be cost prohibitive to update these systems. And without access to source code, it's also cost prohibitive to make incremental patches without sacrificing the safety of that code. Because as we've talked about before, making arbitrary binary transformations is incredibly challenging to verify. So what we want to do here is use graph-based machine learning to recognize the different components or the different parts of control loops that exist or that are implemented in this kind of firmware, so that we can reconstruct what the firmware is doing at a high level from a mathematical standpoint, so that we can re-implement the software easier. So instead of having someone to have to do all of the reverse engineering to figure out what the program does and then re-implement it only with these improvements made, we can essentially lift the algorithms. We can lift the high-level programmer's intent and re-implement from there. So essentially, we're training a graph-based machine learning model to do high-precision reverse engineering. And what we're doing is we're exploiting the fact that most of the time, the implementations for certain types of mathematical operations, they don't vary much. If you're implementing the quadratic equation, there's only so many ways you can write that in code. So ultimately, and there's also even fewer ways that compiles to meaningful code in a binary. So it can be relatively easy to do pattern matching, which machine learning is quite good at. So once again, is this a problem for ML? And here we have no requirement for soundness because we're doing reverse engineering. We've accepted the fact that re-implementation is going to require some kind of expert, but we're trying to essentially reduce the cost, not replace the re-implementation. We're not trying to actually generate sound code. And two, can we get enough data? And the answer here is ultimately yes, we can generate synthetic data set for math constructs easily because we have a large number of implementations from libraries that implement these things. So for example, you use mostly math libraries to do high-level math or implement high-level math constructs like lookup tables, et cetera. You don't necessarily see people implementing these on their own. All right, so what we do for Corpin is we adapt the graph-based machine learning algorithm to a different problem. In this case, we're dealing with binaries. We're not dealing with source code. This presents a problem that we overcome in two ways. The first is for our training data, we use a tool that was developed by Trail of Bits called Mixema, which does binary to LLVM on our lifting. And then we also use synthetic data that we generated from source code, and we just use a compiler to lower it to an intermediate representation and create our data sets. So in this case, we're coming from both ends of the program representation stack, meeting in the middle at intermediate representation. But as you can see, it's mostly the same high-level process. We have labels for our data. It's processed by a piece of compiler infrastructure, or in this case, decompiler infrastructure. We create program dependency graphs. We label them as being these different blocks, these different symbolic mathematical functions, like a summation function, or these three blocks represent a PID controller that would exist in embedded software loops. We create a model to do matching. In this case, we're not doing path matching. We're not matching a path from one point to another path. We're doing subgraph matching. It's a more complex problem. We're finding a subgraph within a larger graph and matching it to something that we consider a known example of a particular type of mathematical construct. So our data strategy here, as I mentioned, had to change quite a bit. So we started off with source code, with source code examples that we generated programmatically to create source code. But ultimately, as I mentioned before, there's only so many ways you can implement these. So we end up with a relatively small amount of data. So one thing that we added to our data processing strategy for this project was to do data set amplification. So we took a relatively small volume of real world samples, and we applied logical and syntax mutations to take these small samples and create many samples that are distinct, but ultimately very similar. And this is ultimately to increase the volume. So let's take a look at what this actually looks like. So if you take a look at how a PID controller might be typically used in your home, your thermostat implements a PID controller. The way your PID controller works is essentially you have a temperature sensor somewhere in your home, usually located on the thermostat itself. You have some control or some processing algorithm that also feeds inputs, which is usually what you set the thermostat to, although in some cases it can be a timer or other things. But ultimately, you have a temperature setting. These two inputs go into a PID controller, which is that small batch of synthetic, or a small batch of mathematics I showed on the previous slide. And ultimately, it turns into an output of 0 or 1, which is turn the heating element on or turn the heating element off to control the temperature in the room. This causes changes in the environment, which causes changes in the temperature sensor, which ultimately is what this feedback loop is what keeps your home at a particular temperature. Now, if you have a relatively large building, like a commercial building, you might have what's called a multi-zone controller, where there's a single thermostat which says, hey, keep the temperature in all the classrooms in this building set to, let's say, 70 degrees. Each room has its own individual thermostat, and each one has their own individual PID controller, their own individual heating elements potentially, or potentially a single heating element, which then change the environment. So we could take the fact that these logical permutations of these blocks in this control loop exist to create our own novel examples. So by implementing a single control loop like this, or single PID controller, we can change this to a 2-zone, 3-zone, ultimately up to an N-zone PID controller, an N-zone environment. And we can do this for other different types of control loops that we attempt to define with Corbin as well. Now, additionally, we've implemented these samples, these relatively small volume of samples in C or C++ source code, but we can also take advantage of syntactic sugar in the language expression to make new examples. So for example, this for loop here, which is pretty standard for loop iterating from 0 to 9, over the variable I, can also be implemented as a while loop listed on the right. These ultimately compile to very similar code, but there are some subtle differences within the machine code that give us distinct samples. So we can take a single piece of source code and ultimately change it in different ways to create a larger number of samples, even though the contrast between the samples is relatively low. The challenge here with these mutations, though, is with both of these mutations, is taking the original set of labels and propagating them to the new components that you've added or to the changes that you've made to the source code. Okay, as I mentioned, our data processing approach is very similar to what we did with Voltchecker, where we perform the subgraph extraction, we label those subgraphs appropriately, and then we train binary classifiers to identify those. But we had to do a couple of unique modifications. Namely, we had to take complex mathematic functions that are handled by libraries, usually like LPACK or libm on Linux systems. And these are implemented as function call nodes, typically in programs, function calls to external libraries. We actually had to simplify and reduce these to make our program dependency graphs more tractable. And we turned those into atomic math operations, but that actually helped our classification significantly. All right, as I mentioned, this is no longer a path matching problem, it's a subgraph matching problem. So another way that we were able to simplify our program dependency graphs was to perform graph condensation. So for example, taking the graph that's depicted on the left, that has a high degree of correlation to the LLVMIR that's associated with the sample. We can remove some of these intermediate nodes that do things that we don't care about for this case. Since we only care about the mathematics, code that's doing loads and stores to memory is ultimately irrelevant for this type of problem. So we can excise these nodes and ultimately get down to the nodes that are labeled, any adjacent nodes and edges that are otherwise relevant. And also if we have multiple nodes that are adjacent to each other that are labeled, we can also condense these down into single nodes in certain cases. So this is one of the ways in which for real world samples, we're able to reduce the overall size of the graphs. When we did path matching, we reduced the size of the graphs by doing the graph cutting. In this case, for subgraph matching, the inference time gets very long, very quick, and training time also becomes intractable if you're trying to train on a large number of subgraphs, because they can be quite large unless you reduce their complexity. All right, so let's look at some of the results. The results on this project was much more mixed because it's a much more complex problem, but ultimately we had strong performance on all of our trained constructs, but this is to be expected because we're essentially testing on a holdout set from our training data. So we, at the very least, were able to verify that with the test set that our models were performing useful inferences, but the question then remains, does it generalize to the real world? So to evaluate this, we used drone autopilot software. We tried to take excerpts from code and try to identify symbolic mathematic constructs, and we had a large number of misclassifications, but there was some limited success. The biggest issue was an assumption we had that LOVMIR that we lifted from program binaries would look similar to LOVMIR that was lowered from source code, and that turned out to be a very bad assumption that we learned the hard way. Ultimately, in this case, we didn't have time to go back and make another attempt as we did with the data augmentation procedure in the first project. So this is now future work for us is to work on potentially using a different kind of binary lifter that lifts to a less complex representation or closer to the machine level representation than LVMIR. So ultimately, we're able to conclude that the approach is viable, but what we built so far isn't going to generalize. But there's reason to hope that further work on this project will produce this. All right, so with that, I want to give you a few takeaways. So if you remember nothing else from this, these are the things to take away about using machine learning models, specifically graph-based machine learning models, to do software analysis. The problem formulation is incredibly important. Our successes in these two areas relied heavily on very focused feature selection. As you mentioned earlier, we tried to identify CWE types that other static analyzers failed to detect, but not CWEs that we couldn't represent with information that we could pull from a program representation. So we didn't try to identify complex memory vulnerabilities with Vultchecker because we didn't include a memory model, is a good example. Also, if you try to use pre-trained models that aren't made for program analysis, you're probably not going to get very much success. So I actually made this slide before our company engaged on a months-long project for the UK government to assess the capabilities of LLMs. So I can actually now say that this word unlikely is much more conclusive that the LLM models are actually quite bad at doing a number of these program analysis tasks, but still not definitive. Maybe future versions will be better or more tightly trained versions. Second key takeaway is that machine learning approaches are ultimately going to be a supplement to, but not a replacement for traditional algorithmic approaches. So as I mentioned in Vultchecker, we didn't outperform state-of-the-art static analysis tools when we looked for like static buffer overflows. We outperformed them for certain types of vulnerabilities, but not all. It's much more compute intensive and much more time intensive to use Vultchecker to find a buffer overflow vulnerability than it is to use a rule-based static analyzer. So in this case, even though Vultchecker had some success, I wouldn't recommend trying to use it for those types of vulnerabilities. You should use it for the vulnerabilities, or you should use, for example, Corbin for mathematical constructs. You should use them for ones that are well suited to the model. And once again, they're not going to be able to find every type of vulnerability just through training. And then finally, we learned the hard way. Synthetic data is an art as much as it is a science. So you'll need to make sure that your synthetic data sets are as real as possible for good results. Otherwise, you'll get a failure to generalize. All right, with that, that's the end, and I'm happy to answer any questions.
So I know this is a question for the industry in general, but building an approach like this, especially for like governments, how do you overcome licensing issues like thou shalt not deconstruct our software clauses and
I mostly use open source software. So for example, when we tried to scrape GitHub, we had to, part of the reason why we found less data than we wanted is because we also had to make sure that the licensing on that open source software allowed us to basically consume it. We basically, in order to make sure we didn't get sued, we looked for projects that had very generous copyleft licenses. So even though there is some open source software out there, if it's limited copyleft or derivative works have to also be made open source. That really wasn't an issue for us because we always intended to open source Vultchecker, but we were very conservative with the types of code that we looked at. But another way around this is also the synthetic data. We had to make it so it's ours, so that eliminates some of the issues.
so even for the intent of the use of the program, like for a PID controller for some proprietary lock thing, that's how you're going to apply it, right?
Yep.
How do you?
Yeah, reverse engineering is a huge gray area. Making sure you have the right legal top cover is a subject of an entirely different presentation.
So not your problem. Right?
Yeah, well, in this case, it was government funded, so
Okay.
we could always say the government told us to do it. In our case, we didn't use any, we used subject matter experts to essentially kind of recreate this stuff, or we used the PX4 drone autopilot software because it is open source. We just compiled it down and then reverse engineered it. We had access to the source code, so it's not real reverse engineering. But yes, if the government ever took this and tried to break vendor lock, it would be up to them to determine their own legality. A big reason why this gets used though is because there's not really anybody to go for. So a lot of times the government will fund small businesses to make prototype technology. They'll get bought up by someone else or they'll go out of business after deploying certain types of technology. And now if you want patches, there's literally no one to even ask to do it because you have to track where they went to go work after that. Once the company's gone, there's no money to pay for data retention. So unless you get lucky and somebody happens to have an old hard drive from their previous employer with that source code on, you're not going to find the source code. So in those cases,
It's also known
Yeah.
to you, right?
yeah, exactly. In those cases, you get away with it because, you know, who's gonna,
Right.
they're gonna reconstitute the company to sue you over? Probably not.
You can go ahead.
Oh, so, in the second part of your tour, you mentioned the reverse engineer those mathematical models or mathematical constructs. Could you give some example of this mathematical?
Yeah, sure.
Yeah.
Okay, so this image right here, I realize it's kind of small, is what's known as a proportional integral and derivative controller. This is essentially like a smoothing type operation. So you can imagine a really primitive thermostat where all you have is a really simple for loop that says, if the temperature is not what I set it to be, then I want you to turn on the heating element. And when the heating element warms the room to what I essentially, when the next, so once the heating element turns on, changes the temperature of the room, then a subsequent iteration of that for loop will then create a different check and it'll turn the heating element off. The problem is if your temperature reading is right on the edge, it tends to pop up, pop down, pop up, pop down. What you don't want is for your thermostat to be kicking on, kicking off, kicking on, kicking off. It ultimately reduces the service life of those components. So what a PID controller does is it essentially performs summation of the inputs, runs those inputs through 3 different mathematical operations that essentially provide smoothing. So what ends up happening is when the temperature sensor is borderline, it continues to operate for a period of time until that temperature has either stopped fluctuating, is no longer within like an error term for like the actual like measurement error of that sensor in the first place. And ultimately, that's probably why you've seen sometimes if you set your thermostat to 70 and it drops to 69, it'll heat. And sometimes you'll see it heat to 71 before it turns off. That's ultimately so your heating element operates for a continuous period, a single continuous period instead of many small continuous periods that are hard on component life. Yes.
So, I mean, obviously, there are a lot of interesting technical details.
Mhm.
Types of machine learning approaches that work, features, so on. But just can you give a few more concrete examples of, you know, features and what are the actual outputs of these models? Are they just,
Yeah, sure.
simple classification? Is it more than that?
Yeah, I did gloss over that a bit. Okay, so this is the graph processing for Bolt checker. So let's ground this in a concrete example. In this case, let's use a double free vulnerability. So a double free vulnerability is a memory corruption vulnerability in C and C++ programs where a program has allocated memory for some use. It decides it doesn't need it anymore. So the programmer uses an instruction called a free instruction that says, hey, you can use this block of memory for something else now. And then actually, let's use after free. It's a little bit easier to understand. So a use after free occurs when later on in the program, somewhere else tries to access that block of memory, which has been deallocated and potentially reused by the machine's dynamic or by the program's dynamic nature. And you're now accessing memory, usually with like an old pointer that you're not supposed to access anymore. It can usually lead to a crash because what ends up happening is the program fetches memory from someplace that it's that no longer represents the data structure it's trying to use. It gets what looks like corrupted data and it just bombs out because the violation or assumptions are violated. Hackers can exploit these types of vulnerabilities by very carefully controlling through a series of interactions with the program what gets put into that memory. and what they know that use after free is going to do to get the program to do something interesting like feed them data that they're not supposed to have access to. So in this case, for this vulnerability type, we define the root cause point as a free instruction. We define a manifestation point as a use instruction or an access of data. And we don't place any constraints on the actual naming or pointer aliasing of those 2 points, because that would require us to include a pointer model, not just a data flow and control flow model into this. So this is essentially future work, but ultimately, even without that, we're able to find it pretty easily. So what ends up happening is when you take a look at your training data, you end up with lots and lots of samples, lots and lots of paths between some pointer being freed and some pointer being used, not necessarily the same pointer or even aliasing pointers. But ultimately, the program or the model is able to figure out from a large number of samples which types of paths through a program from a use and a free represent malicious or vulnerable instances. And a lot of times it's the data flow patterns, how data flows into and how data flows out of those uses and frees that help it identify this. But ultimately, we rely on the classifier to learn this or to infer this over time. So we use a very like unbounded and unrestricted approach and just rely on the fact that we have a large amount of data for it to be able to figure this out. So when you push this through the classification for a novel sample, essentially what you're getting is the classifier is telling you whether or not it thinks that a particular path and more accurately, a particular root cause point or a particular manifestation point, if it believes them to be a true or a false one. So as this processing is going, we have to label every use and every free as a potential root cause and a potential manifestation point. The labeled training data will say some of these are true, some of these are, but everything else is false. So when we're doing a novel sample, everything is a possible. And really what we're doing is we're classifying whether or not individual uses and individual frees are true points or whether they just remain possible points. We trace these back to the original source code lines and we give an alert. Once again, I'll harp on the fact that this does not require soundness because we expect that a user has to look at these alerts anyway and say, okay, this is a real one or this is a fake one. But in looking at our false positive rates, we were able to do it just about as well as for this particular vulnerability, other static analyzers. Yep.
I was wondering, for the feature extraction, can you explain a little bit more about how the structure of the backend is working?
Right, so structured AVEC is a widely used library in data science, machine learning that essentially allows you to feed in. It's usually used for data structures. It's usually used for collections of data, and it basically flattens it into a series of columns like you would expect for traditional machine learning models. So if you're making a machine learning model to predict, like, let's say housing prices, your data is usually a large tabular data. It's got the number of rooms, the zip code it's located in, the quality of the schools nearby. And, after you manipulate this data, you clean it up, you're essentially, you're essentially creating a prediction for price based on where the values for all those columns land. We can't directly do that with like a data structure that says, oh, I have an integer that's 5. I have a memory pointer here. You certainly can't do it with like a graph-like structure. What structured AVEC allows you to do is take a structure and turn it into a vector of values. It performs that flattening and it makes the data look like something that a machine learning model, like just a very straightforward deep neural network trained on a large number of samples, what it would expect to see.
So in these structured algorithms, the goal is to, given a structure, find some pattern in the structure, maybe a path or.
No, you can actually think of it more like a hashing function. It doesn't actually try to enforce or find any structure. It's a way of taking something that is like a free-form object and converting it to a sequence of values in such a way that those values are representative of the space for each of the parameters. So like I said, it's more like a hash function than it is like that. So there is some configuration you can do with structured AVEC, like the number of target parameters or predictive parameters. You can also let it kind of figure it out on its own based on the structure, but it will find a way to, it finds a way to convert
something like a data structure, like a class object that you've defined. It turns it into a sequence of values that looks like housing data or something.
I think that is clear, but I think usually when a structure like a graph, like a input graph like data is fed into machine learning, probably the objective is not to arrive at some, like in terms of in contrasted with the tabular data, like maybe the price of the house. Probably in the graph, maybe the goal is not to maybe predict a certain value, but probably find a structure of data in terms of the application where as to these.
Yeah, so I think what you're getting at is there are other machine learning modeling techniques. Specifically, they're called graph neural networks and other derivatives that also work on graph-based inputs. In this particular case, we use the flattening technique to use a much more straightforward classifier. And we actually suspect this is probably one of the reasons why Corbin failed, because when we dealt with the path matching, path matching problem in Volchecker, it's a little bit closer, a little bit more amenable to the flattening with structured Vec. But we actually, towards the end of the work on Corbin, we're starting to experiment with like message passing, the feed forward graph neural networks that represent graph-based data in a different way for machine learning models. So this is graph-based. We're exploiting the graph-based nature of the program, but it's not. We didn't use a graph neural network for either of these approaches.
Right, well, we're a few minutes over time, so let's thank our speaker. And I don't have any closing notes, so take care and have a good weekend.
You know, we're going around.